So we're still attempting to make sense of calculus and trying to figure a way to explain it. And last time I explained it very horribly. And now I'm trying to explain it much easier. Now, an idea of a limit first let's talk about. And I realized that I didn't talk about limit first, which is my mistake. Should talk about limits first. Limits. Oh, I don't know what happened there. Are an idea that tells us if there is if you get infinitely small here, is there a point that if you go in all directions, usually all directions, there's a point that they direct to? Yes, yes, that's the way you describe it. Yes. Cool. Yeah, I mean, yeah. In a 3D sense, as I wrote down here, it's usually something like this is the definition, where you get some spherical sense and make sure that this line, all the direction goes over here and flows out. Like, let's go to 3D graphing calculators and go to 3D graphing calculators and try to prove my three-dimensional point. And we'll go back to 2D because that's how you're supposed to describe it. Plus z square root of 2 equals 0. Uh, sure, that works out fine for me. I did not realize that turned in. Actually, that makes sense because I can explain that too. Actually, if you zero out the y direction, it turns out. Actually, I can make a sphere here, can't I? But if you zero out the y direction, it should get a parabola because it's x square, and then z square is also if you go this way because z is the up and down. If you look how do you transform this shit around? I want to shift this. Oh, if you shift your view 90 degrees, you can kind of see the parabola in all directions. Um, uh, so I'm not sure why it's not allowing me to leave. Uh, I never thought of just getting going to a 3D graphing calculator and just don't look at that. Why the hell did that not save? Why the hell did that not save? Oh, I didn't save it. Obviously. Also, my this thing is incomplete, so don't even try to. I mean, you can try using it, but it's not going to help you that much. But let's look at this point over here. We may not know it, but if you look at this direction and you come from this direction, this red line is where it's coming from. You can see that over here, that in this spherical bulb that I talked about over here, all the direction collapse at that point, and you can I refuse to deal. You can see that that point the vectors do show that there's some connection. Why I hesitate to say is that it exists. The limit exists, but the point might not exist. That's why I'm not saying that. If I were to give you a certain clause in the whole system where I say that there's a discontinuity where there's a white space over here, the infinitely small white space, and then you get and at that point the red space is over here, or even the red space doesn't exist at all. The limit still exists. The vector still point to something. And now that I think about it, I should talk about vectors in trig. My God, the more I talk, the more I realize you need to know a lot of shit. You need to go back and back and back. And that reminds me, for this section, there is a certain section that I like to talk about because in reality, this is not really that helpful, but it is something you need. But the way you make questions so easily on this thing. The way I make questions is basically although it doesn't show all possible polynomials that can be done by higher levels. To do that, I don't like to make questions like that because you need to use this system to figure it out. Which yeah, if you if yeah, plus 3 x plus 2 me s minus 1. You can always do this to get a simple equation, like going over here and finding a expanded polynomial and giving that as a question easily over here. You can give that as a question. You can always do that, and then you have to figure out by doing this method because we give whole variables. But if you give something like this out, this evil bastard question with the x plus 3, you need to use one of the division methods. Fun fact: I just went on tangents for no reason, which I'm not sure if it's a good thing, but that is the idea of a limit, and then in a 3D-dimensional sense. Did that make sense to everyone? Not sure if it did, but I'm just going for a trial run. So if I were to give, I think I actually pretty much wrapped it up over here. Pretty much. I need to show that. So let me save this again. This is made by me, but I don't have a save file in here about the image because I deleted it because it was too much space. Because I have way too much images in that document. And I need to do something right here. This is not proper notation. I just wrote it to make it easier, but that is definitely not how you write proper notation. If you have to say that there's no limit of this function because it's a function because there's no two line like this, and there's a way to get those limits. I'm just not really pointing it out right now, because there's no necessary need to. If you go over here and say x goes to -1 equal dne, that is the proper notation. This is the proper notation, not this. If you go to one-sided limit over here, which is a completely different. I don't know how I had enough time to do all those. I forgot. Oh yeah, I had enough time because my classes were easy this summer. Oh yeah, that's why. Yeah, right. I'm not sitting here. Um, Again, I'm only showing this because I didn't write enough right notation over here. This is completely wrong. You don't use this notation. I just wrote it there to make it easier. Um, I would personally take that notation, but technically, that is a wrong notation because this indicates a vector, uh, which technically speaking, you are using vector idea of certain kind of vectors, not really a vector, although. So you're just going immensely small to that point to see if there's a direction. So I guess there is a vector because a vector is just a direction with a magnitude, but it's an infinitely small uh, direction. So you can't really say it's a vector, can you? No, you can, I guess. I never thought of it that way. I don't know, actually. You might be able to actually get away with that thinking about it. So what's the difference between the other one? So this actually exists if you're talking about 1D dimensional push. So what that means is like a limit on C. So limit on C, which I don't know what the point is. So let's just say that's 0.21. Is there a limit if I say this? No, it's dne. But if I wrote this minus over here, look at this minus over here. This minus. Oh wait, that's sorry, plus for this one. Let me. If it's plus, it exists, and I don't really know where that is. And if you do limit of x minus, that's d, and there's a direction coming there. And that's why this is so much harder. Do you think there is a directional um, limit? Yes, obviously. Because if you say that it goes from here, you can kind of say there's a directional limit, but what's the use of it? I don't know. We don't really get taught this, and it's kind of useless in a degree. Like, where the hell would you use that? And how the hell would you use that? It's kind of hard. I never actually got taught that. I just thought of it now because, well, you could do analysis, but what's the use of it? I guess you could say that the use of it could be like a wall like this, and say that there's a 1D motion over here. And then you could discover that motion and find that one point. Wow, that's an interesting idea, isn't it? I'm not sure if it's already thought of. Probably is, because limits are heavily discussed. But a three-dimensional map, and then if it directs someone to that point, but in different directions like this, there must be a line or a certain place where that doesn't exist. But if you look at one way or one way this way, it does kind of exist. So that bandwidth would be considered a DNE. But if you were to approach it from a negative, positive, whatever direction you want, it would exist. It's an interesting idea, actually. I wonder if there's already a mathematical notation for it. There probably is. I just never learned it before, actually. I hope I learn it. Oh yeah, there's also the infinite DNE idea, but I don't think we need to know it. I think we need to more talk about Riemann sum, where I basically don't talk enough about it. Right hand or left hand. Yeah, I don't. I think my document here doesn't talk enough about how summation works, because I do talk about summation here. Basically, that's the definition you can think about, but it doesn't really help understand it, and I think you need a voice to understand the integral. But integral is an antiderivative. Oh, and actually, to talk about integral, I need a derivative first. And what is a derivative? Well, a derivative's definition. And there's shortcuts to this. There's easily a lot of shortcuts you have to know slowly by slowly. It's like learning algebra again. Yeah, I should know this by heart actually. Why am I thinking so hard? So this has another definition where f phi x equals f x plus h minus f x divided by uh, h. Yeah. This definition and this definition. Wait, are they the same? What am I thinking about? Oh, I'm thinking about this one. So it's f x minus f h divided by x minus h. We can kind of the idea this is a slope. And this is also a slope. That means because the definition means that they have the same answer. Although this is not possible right now because the way we think about the derivative and how we solve it um, will not apply here for now. This is important for physics for estimation. You'll learn in entropy that a lot of the things that we learn can be estimated by just a small slope. because the body of water is too large to actually affect anything. So it's actually easier just to think of the slope instead. All right, so what does this actually mean? Uh, my document is completely useless for it, but I think this over here is a good example because we can talk about the power rule here while going into motion of what I'm talking about. Oh, you could also look at this infinite depth test law here. Um, so again, it's a trial one for me. I'm going to continuously trial, and because trial and error makes perfection. Actually, why am I doing this here? I can. Oh, right. You can't actually see me doing it because I made this into a recording of a screen only, which means I can only show you through Canva this thing. Okay, so actually I can just show over here. So if you look at the highlighted screen, we have x squared, and we are taking a derivative of that. We get into this position. So about a limit, if it plugs in and you get an answer, you leave it, usually. And as you can see, when we did this, we get this formula over here. But something cancels out over here. When something cancels out, you allow it to cancel. So you get this. And the limit of that is 2x because this is 0. And if you plug in h and equals 0, you leave it. You leave it. You just let it go to x. You might be saying, why not just plug it here? Well, that equals 0, right? And the limit of h cannot possibly go to 0, right? So, and there's also a problem of this over here. The bottom, can you divide by 0? No, you can't. You might say that, how about if I get h go to limit to 1? Why not do that? Well, then it wouldn't be a derivative because you're not going to infinitesimally to 0. You need to go to infinitesimally to 0. The whole point is to try to get a line and segment it off to the smallest point. And the smallest point is the idea of 0, the nothingness of a certain situation. So that's why the definition of a limit is a limit going to 0. That's why. And the integral is similar. Right? But yeah. So the limit of h going to 0 is so important because you're getting intimately small point, and that is the idea of getting a tangent line and seeing the change in rate, which is a type of vector. And getting a limit transforms that into a vector, thinking about it. So now actually think about it. No. The equation itself is not a vector, but the if you plug something in and get into that, it does turn to a that's an interesting thought process I just had. I'm not sure how I would describe that, but yeah. So yeah, so invertest is 0. So when we have something like that, actually I don't even know why integral gives you the rate of change. Why does it actually give you the rate of change? Well, if this gives you the magnitude of this change, like this magnitude at that 0 point, you're basically turning that into a line over here, right? Not thinking about that definition works. And that's why summing a small, tiny little bits continuously. That makes perfect sense. That's a good way to teach it. And thinking about it, that works. So if you get a derivative, you're turning that derivative into a line bar. And I don't know how this derivative will turn out. It looks like, and let's just make an easy one. If that's true, we get this is negative x squared, right? So this is 2x negative. So negative 2x is this way. So that will turn to this. So this is a line over here of how fast it can go. Thinking about it. So, and then over here is basically not changing at all. So it's something like over here. And then it goes downwards. Actually, no, that's what. It's like this kind of actually. So since it's not changing at all, something like this, and then this is a 0 point over here, and you would see these lines like this, and which is why how integral works is tiny little summation, and that's how you would kind of have to. You have to refine this. I have to refine this um, way of teaching as part, but it kind of makes sense to me why it works and how and why you would teach this way. So yeah, I just made a lot of things up at the fly. But you by doing this, I actually understand